Hello audience. Today we will discuss about the conducted emissions measurements. Conducted emission compliance requirements during product development or product approval. The term conducted emissions refers to the mechanism that enables electromagnetic energy to be created in an electronic device and coupled to its AC power cord. Similarly, to radiated emissions, the allowable conducted emissions from electronic devices are controlled by regulatory agencies. If a product passes all radiated emissions regulations but fails a conducted emissions test, the product cannot be legally sold. The primary reason that conducted emissions are regulated is that electromagnetic energy that is coupled to a product's power cord can find its way to the entire power distribution network that the product is connected to and use the larger network to radiate more efficiently than the product could by itself. The frequency range where conducted emissions are regulated is typically lower than the frequency range where radiated emissions are regulated. As an engineer in the EMC field, it is important to understand the measurement procedures that are used to measure conducted emissions. Conducted emissions are regulated by the FCC over the frequency range 450 kHz to 30 MHz, and the CIS Prairie 22 conducted emissions limits extend from 150 kHz to 30 MHz. When testing a device for compliance with the FCC and CIS Prairie 22 regulatory limits, a line impedance stabilization network, LASN, must be inserted between the AC power cord of the device under test and the commercial power outlet. Due to the difference in regulated frequency ranges between the FCC and CIS Prairie 22 regulations, the LASNs for the two have similar layouts but the component values are different. As shown in the diagram, the AC power cord of the product under test is plugged into the inputs of the LASN, and the output of the LASN is plugged into the commercial power system outlet. AC power is filtered through the LASN and the product is provided with unpolluted AC power. A spectrum analyzer is connected to the LASN and measures the conducted emissions from the product under test. The purpose of conducted emissions testing is to measure noise currents that exit the product under test's AC power cord and make sure these currents are within the regulated limits. The product under test is connected to a LASN, which stabilizes the impedance seen by the product looking out the AC power cord. The second objective of the LASN is to block external noise that exists on the power system net from entering the product's AC power cord. Any noise currents from the power system net that were to enter the product's AC power cord would add to the conducted emissions from the device. Since we are only interested in the conducted emissions that emanate from the device under test, it is important that the LASN prevent noise from the power system net from entering the product's AC power cord. The LASN must satisfy both of these objectives over the entire conducted emissions frequency range, 450 kHz to 30 MHz for FCC regulations and 150 kHz to 30 MHz for CIS Prairie 22 regulations. Power supply filters. Virtually no electronic products today can comply with conducted emissions regulations without the aid of a power supply filter. Power supply filters are inserted where the power cord exits a device, thus they prevent conducted emissions currents from exiting the device. An important aspect of power supply filters is the fact that they must reduce both the common and differential mode currents from the device they are filtering in order to satisfy conducted emissions regulations. Fast voltages and current changes in DC to DC converters will cause conducted noise on the input of the modular device. Fast rise time and fall time on logic loads will produce conducted noise that also reflects back into the input. Conducted noise will tend to generate electrical and magnetic fields that will radiate noise if circuit runs are not properly configured. Usually good layout and filter design will minimize this effect. EMI reduction solutions. Avoid circuit path runs in large loops, which will act as antennas. Keep close proximity of the power conductors, which will minimize the loop area and keep radiated emissions down as well. An external input and/or output filter may also be needed. If so, then great care must be taken to avoid undesirable effects by the stray inductance and/or capacitance of the filter, which may cause instability or performance degradation in the overall onboard power system. The designer must keep in mind the impedance mismatches between the input filter and power module. One way to prevent this is to ensure that the output impedance of the filter is much smaller than the input impedance of the power module at all frequencies. X capacitors are connected between the line phases and are effective against differential mode. Y capacitors are the EMI capacitors that are connected from the input power feeds to chassis ground and are effective against common mode. Synchronizing power modules has the benefit of eliminating beat frequencies caused by two or more devices operating at frequencies that are close to one another. If we can operate multiple power modules at the same frequency, NEMC emissions generated will have a similar spectral density, making it easier to filter out that particular frequency. Sometimes, turning a power module and/or other magnetics 90 degrees, such as transformers and inductors, can improve EMI performance of a power supply design. Even subtle design changes can cause a power supply to have higher EMI than necessary. Designers need to understand where noise originates and how to reduce it to acceptable levels in the particular system it will serve. You can reach us, with your product's requirement for end-to-end design solutions for EMC compliance. Our design engineers will design EMI-free solutions for your products. You can reach us on info@croydonservice.com or visit us on www.croydonservice.com. Thanking you.